Next up, let's talk about trees. Specifically, let's write a recursive function that draws a 2D fractal tree. You might ask, what is a fractal? So the term fractal refers to a never-ending pattern that repeats itself at different sizes or levels of magnification. In the case of a tree, it's not a never-ending pattern, but it is a recursive pattern that repeats itself at different sizes. So how do we draw a tree? Well, we'll do this using Turtle Graphics, and to begin, we'll start with this provided code. So up at the top, we import the Turtle Graphics library. And again, the Turtle Graphics library isn't really part of this course. It's not a thing I'm ever going to test you on, but it makes a very useful depiction of the concepts that we're trying to cover. So we've imported the Turtle Graphics library, and our main function just initializes the drawing environment. So it creates a screen, sets the drawing frequency, builds a pen, makes sure that we're drawing quickly, hides the turtle so we're drawing just straight lines instead of lines with arrows at the end, picks up the pen and sets it to the bottom of the screen facing upwards, because by default it starts in the middle facing right. So with all that in place, our task is to implement the drawBranch function. So I'm calling it drawBranch here because it's only going to draw one segment at a time, but recursively, that will become a whole tree. If you think about how a tree grows, it starts as a seed, not unlike our function call here, and out sprouts a stem, usually with two little starter leaves on top. That stem is kind of like a branch before the tree has any branches. Then, as it grows, those leaves become branches with leaves of their own, which then become more branches, and so on. So over time we get this full-grown tree, but it retains this implicitly recursive structure. So what we need to implement is this drawBranch function, which is given a pen, which we've called stem here, and a start height. So that's the height of our initial branch, or the trunk of our tree. So one call to this function can draw the first line of our tree, or the trunk, and then spawn two more branches. So we'll call this function twice more, but when we do that, we'll make sure that they're smaller. So if we're given some starting height when we call the initial drawBranch function, then when that branch recurses, we'll make sure to use a smaller height to draw the subsequent branches. So two more calls to this function. Then each one of those branches will draw the next line segment in our tree, and then spawn two more branches, and so on until we have a fully formed tree. Okay, so we need to implement this drawBranch function, and it's given some pen to draw with and some height controlling the length of our line. So let's see if we can't implement the drawBranch function. So the drawBranch function will draw a tree by recursively drawing one branch at a time. We could say its inputs are a turtle called pen, so I'll call this a turtle object, and some number representing the length of our line. This function doesn't return anything, so that's enough. And now, in order to design a recursive function, again, we need to have a recursive case and a base case, and we need something in that recursive case to drive us towards our base case. So let's design this out before we start coding it. So we have this recursive function. We need a base case, which stops our drawing. And we need a recursive case, which draws one segment, one branch of our tree, and then splits into two more branches. So at a high level, that's all this thing is doing. So let's break it down a bit further. In terms of a base case to stop drawing, how do we know that we're done drawing? In this case, the length of the line segment we're going to draw gets smaller and smaller each time we call this function. So in this case, we'll say if the length is so small that we don't need to bother drawing, then we won't draw. We'll just say stop. So we'll return. So we can say if our length is less than or equal to, let's say 3 pixels, then we'll return. So that's our base case. Stop drawing anything, don't do anything, just return. One thing I will say is, in order to make sure that the turtle that's drawing actually pushes the drawing they've done to the canvas, at least to make sure they do it right away, we'll say turtle.update, and then we'll return. Okay, now in the recursive case, there's two things here. We have to draw one segment, and then we have to split. So I'll say, let's break these up. We have the recursive case, which we want to draw one segment, and then we want to split. So to draw one segment, this is just what Turtle Graphics does. So we can just say pen.forward the length of our line. And this will just draw a single line segment. So since our main method starts our pen at the bottom of the screen facing upwards, this is just going to draw a line of length start height, which is initially 200 pixels. just going to draw a line of 200 pixels, and now I need to split to make this thing look like a tree. So if we just drew the trunk, we need to have now two branches, one slightly to the left, one slightly to the right, and then we'll call draw branch in those two directions. So we'll say split, and then we also want to recurse. So the split step here is we're actually taking the turtle object, or the pen, and splitting it into two separate pens. So we'll say split the pen into two pens. And then when we recurse, we're going to recurse on this draw branch function with each pen. So to split the pen into two pens, this is mostly just knowing how to do some turtle things. So I'll say pen2 equals, and then pen.clone takes our first pen, our first turtle object, and just makes a second one in the same spot. This is a bit like our deep copy. It creates a new instance of that thing in memory that's independent, but happens to have the same value. So in this case, it has the same location and the same direction. It's at the top of this branch that we just drew, facing upwards. So now one of these pens should turn to the left, and the other pen should turn to the right. So to do that, we'll just say pen.left, and then we need to give it some amount. So I could say something like 35 degrees, and then pen2 tilts the same amount to the right. And in fact, since this is the same amount for both of these, let's make this a constant. So I'll say tilt equals 35, and down here we'll tilt to the left, and we'll tilt to the right. That way, if we don't like the number 35, we can just change it in a single location, and our whole system will update. Okay, so once we have the two pens cloned, now we have one pen facing to the left, the other facing to the right, and they're both at the top of the trunk now. So now all we need to do is recursively call our draw branch function with each of our pens. So we'll say draw branch with pen 1, and now if we pass in the same length, we're going to end up with an infinite recursion, right? This is going to draw the trunk, and then at the top of that, we'll tilt 35 degrees to the left and draw another trunk. And then we'll tilt 35 degrees to the left again and draw another trunk. And since it's never shrinking, we'll never reach the base case. So what we'd like to do is shrink this a little bit. So we could say, instead of calling it on the same length, we'll say the same length times some number less than 1, so 0.7. And again, actually, let's make this a system constant. So we'll call this shrink equals 0.7, and then length times shrink. So these constants, the first one, start height's pretty clear. The tilt is the degree of rotations between branches, and the shrink is the relative branch length, or the ratio between one branch to the next. Okay, so we've called draw branch to the left, but let's also call draw branch with pen 2 to the right. Now if we do that, it calls draw branch, so we loop back up. We check, is our length small enough? Let's assume it's not. Then we draw another segment. We tilt left and right, so create two new branches from there, and then repeat. So let's see what this draws. So we're calling main, so let's save our code. And we say Python fractal tree. It opens up on a different screen here, and off it goes. So it started with our first branch, the trunk here, and then it said call draw branch to the left, and then to the left, and then to the left, and then to the left, got all the way to here, and then it started filling in. And it started working its way back, and notice it filled this whole subtree before it started any part of this. So that's because it did all of this call to draw branch before finishing it, and then coming back to doing the second one. So it's not quite drawing the way a tree does, where it does one branch, and then two branches, and then four branches. It's doing 1, 1, 1, 1, 1, 1, and then 2, 3, 4, and then coming all the way back to go 2, 3, 4 up this way. And there's our tree. So notice this looks a lot like an actual tree, even though all we used were recursive function calls and straight lines, with a couple of left and right tilts. Interestingly, we can mess around with some of these parameters. So we used a 70% relative branch length and a 35-degree rotation. We can try some other values for these. So let's see what it looks like with a, say, a 60-degree rotation. Run it again. And we get this pretty cool hexagon-looking tree. It's doing the exact same work, just with a different parameter, so it's slightly different shape that it's drawing, but it's drawing all in the same order. And we get something that looks a little bit less like an actual tree, but still pretty cool. This one's fun if you set it to a 90-degree angle. Run it again. And when it's finally done drawing, we get this interesting square-looking tree. We can create a stubbier tree, so if we shrink by a larger amount, so if we go 50% length now each time instead of 70% length, let's close this and draw again. It ends up drawing a lot faster because our tree is shrinking faster, and draws a lot less as well because notice the tree branches shrink a lot faster. The outcome of this drawing, even though it's dependent on the same process, we'll get a different tree each time we use different system parameters. One thing about trees is that they're not in black and white, so let's add a bit of color here. So I'll say down at the bottom we set up our pen, I'll say stem.color is brown, which as you might imagine sets the pen color to brown. But trees aren't entirely brown, they have leaves at the end, so what we'll do here is in our draw branch function, if our length is less than 3 pixels long, we'll stop drawing. But if we're near that, so we could say somewhere between 3 and maybe 7 pixels long, then we'll draw those in a different color, simulating that the edge of the tree should have green color because trees have leaves. We could say if the length is less than or equal to 7, then pen.color is, and then we'll switch it to green. Save and run our code. Actually, before we do that, let's just change the values here. So let's maybe get a different tilt. We'll see what happens if we put a value that's greater than 90 degrees in our tilt, which might seem a bit strange, but let's see what it does. And our shrink, we'll bring it back up somewhere a bit closer, so 0.7 again. And the tree it's drawing is not much like a tree anymore, but the colors are interesting. And when it's done drawing, we get this interesting shape, which it's a good thing we added the color to it because otherwise it would be difficult to see this as a tree. So let's mess with our parameters a bit more. Get a tree-looking thing again. So let's actually make our start height a bit longer, and let's put this back somewhere more reasonable, like 40 degrees. Save and run our code. Oh, maybe a bit too big. Let's make it full screen here. Even at its fastest speed, Turtle Graphics really lives up to its name. But eventually, we get this drawing, which is starting to strongly resemble a tree. Perhaps we should mess with our parameters a bit more to keep it all on the screen, but you can see the edges of that tree now have green edges to resemble leaves. Now, as far as trees go, it's a bit of a scrawny looking thing. Each branch is the same thickness, whereas normally the trunk is quite thick as compared to each successive branch. So let's modify our code again. Let's start by reducing the size of our tree so it doesn't draw so long or so big. Let's split the difference here at 300. And a 40-degree tilt was okay, but let's make it 42 for fun. All right, if we want the thickness of our line segment to be wider at the trunk and thinner at the edges near the leaves, then what we can do is make the thickness a factor of the length, since the length is also shrinking as it goes. So we'll set the color, and we'll also say the pen width is equal to the length, and I'll say divide by 7. This is a number I've learned through doing this demo a few times. Makes a decent ratio of thickness from one branch to the next. So this is narrowing the branches as they shorten. Save and try it out. And when it's done running, we get a tree that looks like this. That looks great. What a difference that makes. The closer the branch is to the trunk, the thicker it is, and it ends up looking quite a bit like an actual tree. Now, the biggest difference between this and an actual tree is the symmetry, I would say. This tree is just far too regular to really resemble anything that would occur in nature. So if we want to add a bit more realism into our tree now, what we can do is add a bit of randomness, a bit of chaos into this order. So let's start by creating a random tilt. So instead of always going exactly 42 degrees to the right and 42 degrees to the left, we'll say each one of these tilts can be within some random range. We'll say the given tilt plus or minus 10 degrees either way. So to do that, we'll come down to our draw branch function here where we have our tilt. And now instead of just tilting the given amount, we're going to use a random amount. So we need to actually import random to start. And now what we need to do is tilt by a random amount that's the given tilt plus or minus some amount. So we could say tilt plus random.randint -10, +10. Or if we wanted, we could say, do the exact same thing in a different way, just for the sake of it. Random.randint tilt -10, tilt +10. Either way works. Whichever seems more clear to you is the one you should use. In fact, just for clarity, I am going to make sure both of them are the same. Take this, put it there. Okay, and let's see what that does to our tree. Save, run it. Still looking pretty consistent. Might need to use a bigger factor here. Plus or minus 10 might not be enough. But you can see the tree is not perfectly regular anymore, so even just the bit of randomness that we have in there is already helping. And when it's done running, we do get something that looks a little bit more random, but there's still quite a bit of symmetry to it. So let's modify our code a bit further. Let's increase the chaos. And in fact, instead of having to type this everywhere, let's create a new variable here. Call this one chaos. And it was 10, but let's set it to 20. And now the random int from negative chaos to positive chaos. So the bigger the number this is, the wider this range will be. Let's save that and see what that does. And when it's done drawing, we get a tree that looks like this, which is getting a little better. It's harder to see the uniformity or the underlying recursive process, but you still see some consistency. For example, these two branches are exactly the same. You can draw a straight line, and then right above those, you can see the next 4 branches came off those, and you can see where the next 4 branches came off those. After that, the chaos starts to take over, and it starts to look a little bit more real. But we can add some more realism to this if we vary the length of our branches a little bit more. So instead of just shrinking by the same amount every time, let's shrink by the same amount plus or minus some chaos as well. So we can just use the same chaos factor. I don't think we need to make a new one, but let's make this a whole number instead of a decimal, and then we'll divide to get the fraction later. So we'll say 70 plus or minus 20 is the amount of shrink, so 70% plus or minus 20, so anywhere between 50% of the previous length and 90% of the previous length is what our shrink will do. So to make that work, we need to change this. So at the moment, this says take the current length and multiply it by 70, so make it 70 times larger, which isn't what we want. We want to say shrink divided by 100. That way we're multiplying by 0.7 instead of by 70. But then we want to add some chaos. So before we divide by 100, we want to factor in this chaos. So we want to take this random amount here, and we'll say shrink plus some random chaos. I'll do that twice. So that'll take the 70 amount, add on some chaos, which will take it anywhere from 50 to 90. And so let's say it came up with 50. This will make it 0.5, and we'll multiply that by the length. But it's random is the important thing, so not all of our lengths will be the same. Let's close our last tree and try again. And when it's done drawing, we get something that looks like this. And now it's starting to look like a real tree. And in fact, if you ran it a second time, we get a completely different looking tree. But let's extend this drawing a little bit further. So one of the remaining consistencies is that at the end of each branch we'll always split off into exactly 2 branches. So let's change our code so that it can split off into either 2 or 3 different branches. So here we're splitting off into another branch. We're penning one to the left, one to the right, and then we're calling draw branch on both of them. So what we're going to do, instead of having 2 hard-coded pens and then 2 separate draw branch calls, is we're going to put that into a loop. We'll start by just doing a loop that runs through twice, and then we'll make it so that that loop can run a random number of times. So step 1 is to make a loop. So we're going to split our pen. It's not necessarily into 2 pens now, but we'll split it into multiple pens. And we'll say for I in range, and for now we'll just go 0 to 2, so exactly 2 branches still. And then we can change that value once we're ready. But now we want to do all of this for each one of these branches. I want to split the pen and then recurse. Okay, so to do this we only need 1 pen at a time. So we'll say, instead of calling it pen2, we'll call it pen copy equals pen.clone. So we'll make a clone of our old pen. And now, currently, let's say we're facing directly up at the end of our trunk. We want to go either left or right, but eventually we're going to have up to 3 different branches. So let's just say, instead of one branch always goes left and the other branch always goes right, let's just say any of these branches can go in either direction up to some range. Now, a way to do this is, if we want, we can turn left by some degrees, but if we turn left by some negative degrees, then we're actually turning to the right, and vice versa. If we turn right by some negative degrees, then we're turning to the left. Actually, I think it's easier to consider it in terms of right, because clockwise tends to mean forwards in terms of degrees. So what we'll do is we'll take this pen copy, and we'll turn it to the right by some amount that's a random number, so random.randint, between negative tilt and positive tilt. And now we don't need this chaos variable here. The random between the 2 tilt values will be fine. So now this tilt becomes the maximum degree of our rotations. 3 All right, now we don't need these 2 pens, so we can get rid of this. And now we only need to draw branch once per each iteration of our loop. So we can get rid of this second call to draw branch and worry just about 1. But since we're in a loop, we're still going to do multiple calls. We're going to pass in pen copy, because this is the one that we've tilted, and it's still going to shrink by some random amount. All right, so now if this works, and we can test it to see, seems to be working. We'll come back to that in a second. So this loop will repeat and draw 1 extra branch for each iteration, and it's going to repeat exactly twice, so we get exactly 2 branches. If we'd like that to be a random value, we can change the upper bound here. Instead of always being twice, we can again say random.randint, and this time we can say it's a random value between 1 to 3. So we can either draw 1 branch, 2 branches, or 3 branches at the end of each branch. Let's save this and see what happens. And when we run it, we get a silly looking tree like this. So let's try it with 2 to 3 branches per run. Now this tree took substantially longer to draw than its predecessors, but the result looks substantially more like an actual tree, and I would say quite a bit distinct from our initial fractal drawing. But note that same underpinning of just a simple recursive rule for drawing each individual branch relative to the last one is all it takes in order to create such wonderful designs. There's one last notable consistency that keeps this tree looking somewhat unrealistic, and that's color. So right now we have just all 1 shade of green throughout the tree and this really ugly shade of brown. So let's come back to our code here and let's fix that. Let's first start by changing the shade of brown. Let's go sienna. So Turtle Graphics has a bunch of built-in color constants that it just recognizes certain words correspond to certain predefined colors. So sienna happens to be one of them, should give us a nicer shade of brown. But now, right now, we're always saying for all of our leaves, they're all the same shade of green. So another way we can define color, now there's a section in our last chapter on simulation where I'll explain more about color. But the gist of it is we can specify a color as 3 numbers representing how much red, green, and blue light are being transmitted through a given pixel. So what we'll do is we'll set our color to a random amount of only green. So if we have 0 red, all green, and 0 blue, this would be what we have already. So it's just a static green color. And in this case, it's a very bright green. So these numbers are between 0 and 1. So let's make a random value that's between, say, 50% and 90%. So a way we can do that is to say random.random, which gives us a value between 0 and 1. And now we need to adjust that range. We could do this with integers and divide again like we did before, but I'm going to show you a slightly different way because you won't always have random integer generators, but most languages have a random float generator between 0 and 1. So to create any random number, in this case, we'll create the range between 0.5 and 0.9. The first thing we need to do is adjust the width of our range. So currently we have a width between 0 and 1, but now we want a width between 0.5 and 0.9. So that's only a distance of 0.4. So we'll say times 0.4. So now if we get a 1 from our random generator, then this will equal 0.4. If we get a 0 from our random generator, that will equal 0. So we have the right width, but we're not in the right location. So we want to shift these values as well. So we want our range to be from 0.5 at the low case and 0.9 at the uppercase. So if we get a 0, we want to add 0.5 to that. If we get a 1, which gave us a 0.4, we'll add 0.5 to that, and it will be 9. So the general format for this is if we have some random number, we'll call it r, and we want to adjust it to a given range between some upper and lower bound. We'll say r times, it's upper minus lower plus lower. So multiply it by the width and then shift by that lower amount, and that'll give you a random number in the range you're looking for. Okay, so that gives us a random green between 0.5 and 0.9. And one other trick I'm going to add is instead of having sticks as our leaves, I'm going to turn on the pen marker in our base case. I'll come to our base case here and I will say pen.showTurtle. So currently as it's just drawing the sticks, which is just the line that the turtle is tracing, but the pen itself can normally be shown on the screen. I have it turned off by default, but at the end of our tree, we're going to turn it on. By default, it's shaped as a little triangle, so en masse, they should look like leaves from a distance. And now because we're drawing these leaves, we don't really need very small branches. So how about, let's say, when we hit the green part, so that's when our pixels are less than 7 and we change our color to some shade of green. Let's make that our base case. So let's just stop there and draw a leaf. So let's take all of this and put it down here. That should save us some runtime as well, which will be nice. All right, let's save and try this out. And off it goes. So we've certainly stepped up the realism since our original trees, but we're still using the same recursive structure. Noting that each one of the line segments in the leaves in this tree corresponds to a single call to our drawBranch function. So now we can see the idea behind using simple recursive rules to create complex fractal drawings. Now, a version of the code which draws this tree is available on the course website, and I strongly encourage you to take some time and play around with this code. See if you can make some similar trees, some more complex trees, or more interesting trees. And most importantly, make sure you understand the recursive nature of the function call itself, as the whole point of this exercise is to demonstrate recursion. And that's it for this video, so I'll talk at you in the next one.